This topic will cover column hydraulic analysis for sizing in Aspen Plus. In the previous topic, Overview of Column Hydraulic Analysis, we have introduced column analysis. In the following two sections, we will introduce two main modes in column analysis: interactive sizing and ratings. Column sizing helps users devise a detailed design of column internals. With that, we can understand a column's processing capacity, avoid a poor design which may lead to unexpected shutdowns, calculate accurate pressure drop, and estimate the capital cost of the column. Doing column sizing with integrated analysis in Aspen Plus is necessary because thermodynamic information such as vapor and liquid loading and physical properties is required for hydraulic analysis. With this integrated analysis, the designer can improve the accuracy of predictions while gaining insight into column operation. Column analysis is interactive, meaning that it automatically sizes the column and updates geometry dimensions and hydraulic results according to vapor-liquid traffic and user inputs. For example, after a user inputs the geometry of the column internals, the hydraulic plots will automatically update. There are two ways of configuring the internals in column analysis. One way is navigating to the column design ribbon and clicking on the internals button. The other way is going to the specification sheet of RadFrac and clicking the Design and Specify Column Internals button. Multiple column configurations can be created in the Column Internals Object Manager, and a user can select which one will be used for the design basis. The sizing calculation can be performed after column hydraulic data is computed by RadFrac. The sizing calculations do not affect column separation by default since they only supplement the calculations. When vendor correlations are available, column analysis will use that as the calculation basis. If not, well-established literature methods will be used. By default, for a trade internal type, the diameter is calculated to meet an 80% jet flood limit. Downcomers are sized to meet an 80% downcomer choke flood limit, and the number of passes are adjusted based on their wear loading limit. 3-pass trays are skipped during sizing due to their asymmetry and tendency for operational issues. For a packed internal type, the diameter is calculated to meet an 80% maximum capacity limit, and the height is input by the user. The height is determined by the available height in a revamp, or it is provided by the vendor in the form of HETP. Packed internals use the Aspen-Wallace correlation to calculate pressure drop. This is the default selection for most packing types. More detailed information can be found by pressing F1 for help. Multiple sections of a column can be uniquely designed. For instance, the stages above the feed point may be designed differently than the stages below the feed point. In a recommended workflow, column analysis can auto-section the column to obtain the initial design. Then the high-level configuration, such as internal type and section diameters, can be set up. Lastly, the design can be refined further by determining the design parameters. In column analysis, the geometry details can be selected under the View button, and the design parameters form can specify the design assumptions. In the Geometry and Design Details window, we can modify the main geometry configuration, including the tray types, downcomer width, wear length, wear height, and downcomer clearance. The design parameters form, accessed from the geometry sheet, sets criteria for sizing, sets limits for hydraulic plots, defines design factors, and defines correlations used for weeping, jet flood, and maximum downcomer loading. The sizing results are displayed under Section Results. Detailed stage-by-stage results can be seen by clicking By Tray. In the tray hydraulic results, column analysis reports percent jet flood, pressure drop, downcomer backup, liquid mass flow rate or liquid volume flow rate, FS factor and CS factor, approach to system limit, height over weird and assorted downcomer results. While for packed type hydraulic results include packed height, percent capacity, pressure drop per unit height, frictional, liquid holdup, liquid velocity, FS factor, and CS factor, and approach to system limit. The tray stability diagram is important to understanding the hydraulic results. It shows operating flow rates along with boundaries of the stable operating region. Boundaries are based on limits specified on the design parameters sheet, such as a weeping limit, a specified jet flood limit, or a downcomer backup limit. Hydraulic plot results include the overall stage view, tray stability diagram, downcomer loading and wear loading plots, and a carousel of stage plots. In the stage view, yellow and red stage colors show stages that are near stable operating limits or are outside of stable operating limits, respectively. The tray stability diagram can help you understand if the column is or will operate in a stable operating region. In the carousel of stage plots, you can click on the warning or error symbol to see the descriptive messages and recommendations for each stage. In this demo, we'll utilize the interactive sizing capabilities of column analysis to achieve an initial design for a distillation column and use the visual cues and messaging to alter the design to meet hydraulic constraints. Double-click the RadFrac block HCl-COL. From the top ribbon Column Design, click Hydraulic Plots. From the stage view on the left, we can notice about half of the stages below the feed stream contain errors, which are displayed in red. Go to the vapor view. We can see that vapor flow rate is less than the minimum limit of vapor flow for those stages. The same problem can be seen from liquid view. Click Stage with Errors Warnings. Using Carousel of Stage Plots, this indicates that stages 35 to 49 have weeping detected. Now we have to resize the column to remove these errors. Utilizing two tabs is extremely beneficial here. Display the hydraulic plots on one tab and the geometry form on the other. That way, you can see the hydraulic plots update as you are updating the geometry in interactive sizing mode. For top sections, CS1, change the diameter to 4.3 feet. For the second section, increase the number of passes to 4 and increase diameter to 4.3 feet. Now only warning messages are left. Click CS1 Design Parameters. Set the maximum % jet flood to 80 and maximum downcomer backup to 65. These numbers are widely adopted in practice. Set the same parameters for CS2. Now we can view the results. The overall summary for the column internals performance is shown on the column hydraulics results sheet. Note that the maximum % approach to flood is 79.8% in the top section at stage 20. Click on the view for individual sections to view the detailed results for each section. On the summary sheet of each section, you can view the other key performance parameters, such as maximum % downcomer backup, aerated. For this column, the maximum % downcomer backup aerated is in stage 20 of the top section with 37%. Detailed tray information can be seen in the by tray sheet.